Today I got one more topic, and we also talk about the exam. I will post the exam no later than Thursday, most likely Wednesday. And I've given you guys the weekend to do it. So it will be 1 hour. The only limit is that you have to do it continuously for 1 hour, finish it. That's the only limit. I'm pretty sure a lot of you will finish like half an hour maybe. It will be multiple choice, true and false, short answers. So short answers will describe something. So that will be, there's no penalty for wrong answer. So whatever answer, you just make your best guess. Don't leave it blank, because leaving blank, you get 0 credits. Make your best guess. Odds are you may be correct, right? I always encourage you to make your best guess. Even though you have 0 idea, just pick C. Means correct. Right? Don't pick F. Usually I don't have Fs on my multiple choice. I have A, B, C, Ds. Pick one, most likely. So there's no penalty. I noticed over the years, always somebody just leave it blank for some reason. Maybe in high school, earlier, they have penalties for wrong answers. So that's about the exam. I will post it like I said, Wednesday. So on Wednesday, when we having our lab session, hopefully we already have that lab. The exam. All right, that's any questions about also your midterm grades will be determined by this one test. So it will be a temporary grade, midterm. I think you can get your midterm grade online on October 14th, if I remember correctly. So you will get that online. But today we're going, any questions before we move on to today's new material?
When did you say the exam was?
Exam will be, I posted on Wednesday, for example. I give you guys 1 hour. You have the whole weekend, Friday, Saturday to do it. So I'll give you 2 days to do the exam. But you have to complete it within an hour. That's only limit for this midterm.
And the exam will cover chapter 1 through 6?
6, yes, that's okay. Right. Today we're going to do our last chapter, optical sensors. Optical. We have a couple of topics, 4 topics. 4 topics. So the first topic will be the 5 topics, actually. The first 4, this is the 5th. The first 4 topics will be 4 different types of optical sensor. The number 5 will be source, and another topic, number 6 topics, will be the applications of all those sensors and lasers. So 6 topics for today. Let's go directly to topic number 1. So the optical sensor is everywhere. You'll have those, maybe a dozen of those around your house. I put a lot of those. The most common is called the photoconductive sensors. The photoconductive sensors are a variable resistor. So it's a variable resistor. So it's a resistor. The resistance varies with external light. There are many different types. The author put 4 different types over here. Those are the photoconductive sensors. And these are the time constants. That's how long it takes to respond. Looks like they are very fast, milliseconds. So in milliseconds, in this case, 100 milliseconds, it will respond. So fast response. So it's quick compared with temperature sensor. And those are the sensitive range. Some are more sensitive to infrared. Some are more sensitive to visible, the spectrums. Of course, those are the spectrums. If you're interested in a little bit of background physics, so these are the visible. So it's only a small slice is visible to human eye. That's enough for us to survive during the day, right? At night, it's you probably get eaten by lions, 1,000 years ago in the forest, if you're not careful. But the lions cannot see infrared either. So infrared is almost like night vision, because everything have temperature, will visible that way. I'm surprised we don't have infrared vision because that would be perfect because the living creatures are all warm-blooded, majority of those, at least the big dangerous ones. Okay, yeah, if you have that, you will be survive. But ultraviolet, that's another. And but this small, we only sensitive. Human is only sensitive for the small slice of the light, very different type. And this is how the resistance varies with the intensity of light. So the intensity increase, it turned out the resistance actually drops sharply. So if you look at this, it's almost identical to the thermal resistors. If you remember the thermal resistor, it turned out it's the same principle. Thermal is a radiation, is a energy, represents some kind of energy. So the light is also energy. So as energy goes up, this semiconductive device will generate this material, the resistance will drop sharply. So that is, these are the most popular. We will do a demo on Wednesday. That's the, for example, your outdoor security lights. Those are controlled by. So if you look at your outdoor security lights, there is a photo cell, what they call it, cell or whatever name. It's photoconductive. So that is the sensor. So when it gets dark, this sensor resistance will goes up, and the electrical circuit will pick up that sensor resistance and turn on the lights. So when the in the early mornings, light get brighter and brighter, it will turn off lights again. So this will be automatic security lights. Very, very common and very inexpensive. So that's our first sensor. Because it's a variable resistor, so generally we will use a bridge or a voltage divider. So for signal conditioning, signal conditioning, that is how the sensor is connected to other part of electrical circuits. For signal conditioning, we use a voltage divider or bridge. Voltage divider need a total of 2 resistors. A bridge need a total of 4 resistors. So it depends. They all work. So that's our first topic. Second one will be the photovoltaic. Now, photovoltaic is basically a little photo battery, solar power. So it will convert solar energy or light energy into voltage. So it's a little tiny. So I have an example. We will do a demo here. Right here, I have a photovoltaic sensor. If you look closer, the little battery right in the middle, the dark part, that's the little battery. How many? 8 by 8, 64. So in this little sensor, it has 64 little batteries. So when you have lights, these little battery will convert into voltages, those lights into voltages. So the intensity, the higher intensity of your lights, the higher the voltage output, each 64 of those. So that's a photovoltaic. So what is a photovoltaic? It's a variable voltage. Right, variable voltage. So the sensor's output is a variable voltage. It's directly proportional to intensity. So the higher intensity, the higher the voltage. So if it's voltage, it's perfect. The signal conditioning will be much easier. All we need is the amplifiers. We can have 2 or 3 amplifiers to do the signal conditioning. The signal conditioning, we don't need a bridge, we don't need a voltage divider because it's already voltage. That's perfect, we like voltage. The amplifier, the perfect input for any amplifier will be voltage. So this is the voltage, output will be voltage. So that's for the signal conditioning part. That's another example of a physical signal conditioning. This one will do a couple of math. Why we need to do the math? Because we prefer the output to be, for example, 0.5 to 1.2 watts. So the output will go from 0.5 to 1.2. That's the requirement. I want this. When the light changes over here, I want the output to go from 0.5 to 1.2. So you do this math operation. That's the addition. Subtraction. Yeah, that's subtraction. Positive subtract negative. This is amplification. The gain is determined by the resistors. This is a constant. We will provide a constant. Whatever number we want to subtract this result. So it's all math. This is a mathematical equation represented by electrical circuits. So electrical circuits, that's the equivalent of a mathematical equation. So that's our second type. So first is photoconductive, second is photovoltaic. The next one will be photodiode or phototransistors. Those are 2 similar ones. Either a photodiode, or we will do a demo again this Wednesday. Let me give you an example of a photo transistor. That's a phototransistor right there. It's called S. That's a LED. So this is a transceiver. One side is LED, it sends out light. The other side is a phototransistor. So this side is phototransistor. So it will read the whatever target So if you have a box passes by, if you have in the assembly line, this will count how many box of products passes by, because the LED goes here, bouncing back, and sensor will pick up So we will do one of those demos, just like the assembly line, in the assembly line scenario. So diode, the light will be acted as a switch. So this light will turn the LED on and off. Remember, the LED is a one-way switch, And this light will just turn on this one-way switch, close and open this one-way switch. Of course, there's a threshold of lights. So if light is too dark, it cannot turn this LED on. Same thing for the transistor. That's acted as a switch. This is the turning on and off part. So the light here will turn this switch on and off. So the output will read. So if the switch is off, the output will be high voltage because it's off. So high voltage. What happens if the switch is closed? It's short to the ground, the output will be 0. So the light will basically control the switch on and off. By control the switch on and off, the voltage output voltage will vary, go from VCC to 0, VCC 0, VCC 0. So that can be picked up by computers. That is almost similar to, for example, fiber optic communication. So when we use computers, talk to each other, many times, or audio, I have a speaker I wired with a fiber. So on one side of the fiber, I have LED. On the other side of the fiber, I have this. That's this. And when I'm flashing my LED on and off, this will pick up the code. And then if I have a protocol, what do we mean protocol? Protocol means agreement. So you receive a bunch of 0, 1s. What exactly does it mean? It is defined by protocol. So once we set the protocol, for example, it's a USB protocol, it's an Ethernet protocol, it's a Wi-Fi protocol, it's a SONET. In the case of internet backbone, everybody is wondering, what is the internet? The internet backbone, that's the like the high-speed superhighway of internet is a SONET. So this is the technology Internet's used today for the fiber optic. So it's just a bunch of 0, 1s. To make exactly what does it mean, you have to have a protocol. The protocol defines the meaning of all the 0s and 1s. So that's a photo transistor. Well, photo sensors everywhere. For example, if you have a digital camera, what is the picture sensor or image sensor? The image sensor is just light sensors. How many? 10 billion or 14 billion or 20 billion. So if you buy a digital camera or buy a cell phone, the salesperson says, this camera has 20 billion pixels. What does it mean? That means 20 billion light sensors. If it's color image, 20 billion multiplies 3, because you need to have the red sensor, the green sensor, and the blue sensor. So if it's 20 billion pixel, it means 60 billion light sensors. That's the most common light sensor you use every day. When you take a picture, each of those sensors will convert the lights, a small, tiny dot of lights, and then you create an image. When you have 20 billion of those, right? 20 billions as a matrix. So 20 billion means 5,000 by 4,000. That's 20 billion. 5,000. So you will have 5,000 horizontal, 5,000 vertical. That matrix will be 20 billion. So obviously those sensors are everywhere. None. The last sensor will be an old type, very old, but it is still the most sensitive light sensor. It's the most sensitive. It will pick up, in an extreme case, a couple of photons. Photon means the smallest amount of light, and we call photon, smallest amount. And this one single photon, for example, will be picked up by this sensor, can be picked up. How can they do it? Because the multiplier effects. This sensor generally is multiple of them work together. So, for example, one light photon hit our target, its energy, and it will when you think about you throw a stone on the water will splash, right? Same thing happens here. You throw a photon in your target, actually accelerate. You accelerate it. The first stage is not, you will splash electrons. So there's billions of electrons, just like oceans of electrons. Think about the lake, oceans of water. This is oceans of electrons. When you throw a photon, like a stone, into this ocean of electrons, what happens? Some electrons will be flashed out, bumped out. And those electrons will accelerate, hit a second target. So suppose they have one photon, 3 electrons bumped out. Those 3 electrons will be accelerated, hit the new target. It will create multiply effect. 9 electrons will come out. 9 hit another target, 27. So multiply. What happens if you do it 10 times? If you do it 10 times, it will be 3 to the power of 10. 3 to the power of 10. So it will multiply thousands of times, tens of thousands of times. 3 to the power of 10 means tens of thousands of times amplification. So this sensor is extremely sensitive. So if you need extreme sensitive scientific experiment, so this is generally used in the scientific settings. You are measuring extremely dark objects from the universe. So that's the first 4 topic, 4 different type of sensors. Out of the 4 different type of sensors, those 3 are very popular, extremely popular. They are everywhere. This type is also billions of them as cameras. So the camera is that's the billions of photo transistors. 20 billion, for example, 30 is 60 billion. So those are the popular ones, extremely popular. The modern electronics need to detect light, and those are and the last one is the most sensitive. although it's old technology, it is extremely sensitive. So now we move on. Our fifth topic will be the source of our light. Light source is everywhere. LED lights. Relatively new light source is called a laser. So this is how we create light. This is the physics. This is so far our understanding why something will emit light. Our understanding is in physics, each atoms has electrons. Those electrons will have energy. When the electron goes from high energy to low energy states, light will emit it. So there's an energy difference. That difference will be 1 photon. So when electrons go from here to here, it will radiate 1 photon. What happens if another photon goes into the atom? The electrons will bump up to high energy states. In some extreme case, the electron will break free of the atom, became free electrons. That is the case for this application. So those electrons, when we hit it by a photon, it will break free from the atom. So that's our understanding of the electrons. These electrons were free by the radiation. That's the radiation. The electrons go from here to here, high energy states to low energy state. It will radiate 1 photon. That's physics. Maybe 10 years later, this will be completely incorrect. That's the current theory. Currently, that's our current understanding of how light is created. So we also can create the laser. Laser is a special kind of light. Does not exist in nature. That's something quite a claim because nature is huge. You never see. The universe is the big, unbelievably. So far we consider it's only man-made laser. So the lasers are a special kind of light. All the photons are identical. The phase angles, the directions, everything is uniform. Everything is identical. So that's laser. I found we have very good background on laser because I have exam problems about laser. Everybody got it right. So laser is a special kind of light. First is monochromatic. That means all photons are identical, one color, one wavelength. It's coherent. So that means the goals remain coherent. Divergence means the angles. The beam has a little divergence. So to be considered as laser, the divergence has to be smaller than this. Of course, the smaller the better, the divergence. That means if you hit a target, for example, we put a mirror on moon. on the surface of moon. So I guess in the 60s, in the 70s, astronauts put a mirror right there on the surface of moon. So today we still can point the laser and it will reflect right back to Earth. That's power. So laser output power, generally for consumer electronics, we don't need a lot of laser power. We just need milliwatts. Those are the type of laser source we use our different applications. For example, the DVD players, the laser pointers. Sometimes some people use those. Okay, that's something about laser. Besides laser, we have many others. We just skip that. So next we will have four applications of the application number one called pyrometers. Pyrometers is something we use quite often, especially today. For example, when you enter some buildings, you require to measure temperature. So they will just point something on your forehead. That's measuring temperature. So it's measuring temperature without touching. How can you measure temperature? The old thermometers are all conductive type. So you have to have the sensor physically touch the target. The sensor have to be physically touching your target. For example, we will do, you guys need to buy a thermocouple. But in order to measure temperature, that thermocouple have to be physically in contact with the target. Unlike those type of sensors, these pyrometers use radiations. Radiation can be narrowband radiation, can be broadband radiation. It doesn't matter. Mostly is infrared radiation because the temperature, the hotter the temperature, the more infrared energy radiation, the stronger the infrared radiation. So what happens is up front you have infrared lens. This is the infrared lens. So this infrared lens kind of dark looking, so it's not transparent. Not like your camera lens. Your camera lens is a visible light lens. This is a infrared lens. They do the same, exactly the same purpose, concentrate out the energy. Because the infrared kind of weak, you need to concentration. So once the energy is concentrated right here, so you have a lens. The lens can be reflective. This will be reflective lens. That works. It can also be the type of lens up there. So this is reflective. The lens will concentrate all the radiation to a sensor. And the sensor will be, for example, photovoltaic. Can be a transistor or can be a diode, can be photoconductive. I'm not sure what type they use inside. One of those. So one of those sensors will pick up the intensity of infrared, and at the other part of the electrical circuit will do some calculations and display temperature. So it will be very nice because it's It's very fast. I have one of those around my house. So I always measure temperature. For example, during the summer, I will put a blade outside my west-facing windows. During summer, those west-facing windows are so hot. It's like so hot. So you need to put something outside. I put something outside, cover. It works perfectly. After I covered it, I measure temperature of the windows. It will be much cooler. So those are sensors. Those are application number one. The second application, so application number one will be the pyrometers, especially infrared pyrometers. Those are called broadband because we don't care about the strength of particular color of light. So generally, our application is broadband. In some special case, we might need a narrow band, but when we measure temperature, we don't want narrow band. We want broadband. We want more energy. We want the sensitivity. We don't want narrow. So that's our first application. There are three more applications. The three more application is actually one section. So the first application is section 5. The remaining three application is a section on section 6. So let's look at those applications. The first application will be label inspections. Those are very common in today's assembly line. Everything became automatic. So you have to pick so this is the assembly line. So these sensors will be picking up this target, a couple of sensors. Some will be the position. Some will read the labels. Yeah, you have positions, you have labels. The labels can be coded. So once the label is kind of a binary, dark and on Wednesday, our lab demo will be similar. We will have a label we will read. So this is the same thing. When the target moves, you can read labels. Can also read positions, also the dimensions of the object. So anyway, in this assembly examples, this type of sensor is very, very common. It's the input will go to a computer, and the computer will decide, can be counting the boxes, can read the labels, can do whatever you want to do with your target. The second example will be turbidity. That's measure the purity of your water. So this is, for example, your sewer or whatever product can also be whatever liquid. So, for example, Coke. So this is a quality check of your drink or whatever product. And this is the reference. This will be your product. So if your product the quality is good, it will be same turbidity as reference. Otherwise, you might be too dark and too light, and you need to change the ingredients. Those products cannot do not meet the requirement. So that's in the production line. This is a simple device. Compare your product with a reference, and the control circuit will make a decision. So if a good product, it will go to the bottling process. If it's not good product, it may pumping back back to the tank. So you will readjust the ingredients to make it same quality. So you have consistent product came out of this pump. So that's our second example. The third example is also very, very common. We did that with ultrasound last week. We can also do the ranging. The sound travels 300 yards per minute. How about light? Light travels 10,000 times faster than sound. 1,000,000 times faster. So light travels 1,000,000 times, not 10,000, 1,000,000. So that's how fast light travels, 1,000,000 times faster than sound. What does that imply? That implies we can measure very long distance. For example, if we put a mirror on moon, on the surface of a moon, we can measure the distance of moon extremely accurately using the same principle. So that's the speed of light, that's the time. So we can send out a short burst of light and we count time. And the speed of light multiply time divided by 2 because it's round trip. So round trip, so you divide by 2, that will be the distance. Because the light travels so fast, so we need to measure time very accurately. How accurate? At least nanosecond. So that's the speed of light. Multiply 1 nanosecond. So that's how far light travels in 1 nanosecond. In 1 nanosecond, light travels 0.3 meter. That is almost 1 feet. So think about it. Light travels 1 feet. That's almost from here to here. That's how far light travels in 1 nanosecond. Did you guys see that the YouTube video about the video of light traveling forward? So they shoot videos faster than 1 nanosecond. For example, if you can manage to shoot 10 pictures within 1 nanosecond, what does that imply? 10 pictures, 1 nanosecond. That means when you have a short burst of light, go from here to here, the camera actually captures 10 pictures. 1 picture, 2 pictures, 3 pictures, 4, 5, 6, 7, 8, 9, 10. So you can make a movie of a light burst travel from here to here. They actually made a lot of videos, amazing videos. I kind of really enjoyed looking at those videos. Anyway, when we can measure time in terms of nanoseconds, it turned out modern computers are super fast. It is capable. For example, if my clock speed is 1 gigahertz, what does that imply? That implies 1 multiplied 10 to the power of 9 hertz. That means every clock is 1 nanosecond. That's exactly what we wanted. My computer is a 1 nanosecond computer. And it will see the differences in nanoseconds. That's exactly what we wanted. So the modern electronics is nanoseconds. If 1 gigahertz circuit, 1 gigahertz computer means my transistors are switching on and off at 1 nanosecond. That means I can detect something changes 1 nanosecond. So that implies it can measure up to 1 feet, the accuracy. The accuracy of a cutting edge laser rangefinder will be probably 1 feet. 1 feet. So think about it. When we measure the distance from Earth to solar, not solar, the Earth to moon, we can actually constantly measure it. Accuracy is up to a feet, the differences. But we know exactly how far the moon are. Close to yards or feet. I'm not sure how accurate the current technologies are. There are many limiting factors when we do this. But in theory, that's all in theory. In reality, I don't know. In reality. Okay, that is all the subjects we want to cover. There is a little calculation. This can be one of those exam problems. The exam will be posted this Wednesday, for example. So that can be one exam problem. So if I say the object is 300 meters away, what will be the round trip? How long it takes for the light? How long does it take for light to travel round trip? So you will use this equation. Round trip means 2 multiplied 300 meters by 600 meters. That's the speed of light. Distance divided by speed is the time. So 300 meters. What is 300 meters? 300 meters is a 300 yard. It's like a par 3. If you go to golf course, not par 3, par 4, right? A short par 4. Those are kind of the distance Tiger Woods can get hole-in-one, right? I'm not sure anybody get hole-in-one. Anyway, 300 yards away. It's only take 2 microseconds. So it's pretty long time for computer. Computer can measure that very easily. 2 microseconds. The computer is like get really bored. For 2 microseconds, computer can do billions of operations. The supercomputer. So that's like years for computer. Computer is thinking like waiting for years. The time scale is all different. We measure scale subjectively. Our scale is our lifetime. So we live, for example, for our lifetime, so we measure generations, for example, it's a long time, 1 generation. But for the universe, a million years is just 1 second, right? So in that kind of scale, for computers, a microsecond is maybe a year. So computer is very, very fast. So that's all I want to talk about for chapter 6. That will be our last chapter for midterm exam. The midterm exam will cover all 6 chapters from chapter 1 to chapter 6. The majority, I will tend to have maybe at least half multiple choice. Another half will be short answers, true and false, fill in the blank. I have all those maybe. I'm still working on this test problems. So, like I said, post it no later than Thursday, and give you guys Friday and Saturday 2 days to work on the midterm. Our requirement is first, you need to do it by yourself. That's obvious. Second, 1 hour. I will put a timer on the exam. So as long as you start working on this, you have 1 hour. All right. That's all I have for today. Any comments? Anybody?
All right. Well, thank you.
Thank you, Craig.
Definitely not necessarily looking forward to that exam, but you know.
Yeah. I got it. I was a student too. Yeah. I was a student for like 20 years.
20 years.
Straight.
A long time.
Straight. Never go out of school. Since I'm 6 years old, all the way to 26 years old. 26 years old.
I feel like that's going to be me for here soon. Well, I turn 25 next year, so yeah.
All right. Yes. 1 more year. Life after school is much better than life in school. That's what I realized. I should have been in school for such a long time. I was so stupid. not something I want to say, but I was